Now, around a month ago, in April, something really exciting happened. And no one really knew about this until it flooded everyone's Facebook's timeline, your Instagram stories, and was all over the media. And that was where we got this image. The first photograph of the event crossing horizon at a black hole, right at the center of it. Now, this was incredibly exciting for scientists and scholars, but also for general people alike, because we got the world together to do something that had never been done before. We pictured a black hole at the epicenter. Now, this has implications not just for the preliminary stages of science, but onwards into the future, because we can now map what happens inside a black hole, what the behavior of the structure is like, and position different specimens to enter into it and understand what the behavior of it would be like. We don't have to do this computationally anymore, we can see it live. Now, what events like this actually do is that they bring humanity together in a very unique way. In the 1970s and 1980s, when we started putting men into the moon, when we started launching many more satellites into space, and even as you transition into the world today, you'll find scholars like Jeff Bezos, Elon Musk, and all of these entrepreneurs exciting the world about making life a multiplanetary species. But what does that really mean? Like, we see SpaceX launching all of its satellites all the time, and we see all of these rockets being reformed to deliver that cargo. But what does this mean for the future of humanity? Well, if we take the trends just periodically over time, we notice that humanity gets excited when space travel occurs. We get excited because we all get to unite over something and collaborate over it and bring it together. But this transcends further into the new trends that are taking place in physics today. There are different things that are exciting people, and it's no longer just the idea of bringing mankind to Mars or the idea of bringing mankind into space and exploring further. It's the idea of discovering new worlds. That is to say, in the 1980s and the 1990s, we didn't actually know if there were other planets outside of the 8 that orbit our solar system. That seems crazy to think about today, but we weren't sure if there were other planets outside. And the first discoveries that were made, they were usually vetted off as saying these were other astronomical objects like comets orbiting or different anomalies in the system that accounted for these different shifts. But that wasn't the case in the 1990s, when a professor at Harvard, David Charbonneau, first in the parking lot of Harvard University, took his telescope, pointed up into the sky, and said, there's likely a planet orbiting this star, but we don't know for sure. How can we figure it out? And this seems trivial to say because in space today, there's so many different objects. You could go through a list. It wouldn't just be these different planets that you see right here. There could be stars orbiting around them. There could be other astronomical objects causing these anomalies. So how can we know for sure if something that we identify in space is going to be a planet or not? After all, let me paint the picture for how hard this really is. It's like trying to find a wasp crossing in front of the headlights of a car, but doing that from trillions and trillions of miles away, through the observatories in Chile and in Hawaii and in South Africa. So how can we really know for sure? Well, that's where they came up with a nifty strategy to do this, and this is called using light curves to identify via transits. Now, this all sounds really complicated, but let me break this down quite simply. So when you have a planet orbiting in front of its mother star, and you're looking at it from the same plane, that is, you're looking at it straight on through these satellites, then you can see these planets pass in front of the star, and if you're tracking the brightness of the light that comes to you from that star, then you'll notice those periodic dips that are happening over time. That's because the planet is blocking the light from the star from getting into your satellite. And if those dips are happening periodically enough, that is, they're occurring, let's say, once a month, then you can conclude that this planet's orbit around its mother star is happening once a month. So all of these periodic transits are collected through 2 key satellites in space. One's called Kepler, which functioned until 2009, and then onwards from that, we had MIT's new satellite called TESS. And all of them are positioned to look at different sectors of the universe and look at different host stars and see if you're going to get these threshold crossing events like this happen over time. And every single time you do, you ping it. You say, this is one. And if it happens again, you ping it again. And you keep doing this to see how many happen over a month, and eventually you can start to say, hey, this is happening periodically enough. We can gauge with a high degree of certainty that there's probably a planet there. And then you can follow up that through direct measurements taken at instruments and telescopes in Hawaii and Chile and different parts of the world, and you can get them to actually point and take pictures of it and say, yeah, this is probably a planet orbiting. Now, this is just one of the methods. There's also gravitational microlensing and different statistical models that you can use to picture out a planet. But here's why this is really exciting. It says something about how we recognize patterns that wasn't done before, specifically in regards to artificial intelligence. And now, when we think about artificial intelligence, we usually think of this like linear pathway in which humans, which were once evolved from gorillas, are sort of going to encompass AI and take on it, and it'll amplify our ability to do things. But there is an ethical debate around the fear of AI. That is to say that AI will actually replace jobs and cause a divide between humanity, between those who are more specially and technically inclined, and those layman people who won't understand AI, but will use it. So there is this divisiveness element of AI, but what science does is a lot more beautiful than that. It brings AI together to sort of unite humanity. Because I mentioned at the start, as if you recall, that science brings humanity together. Now, what if we could couple AI to use that to help amplify science and therefore bring humanity together in a deeper way? Now, that's exactly what we did at Harvard through our research. We're trying to find different exoplanets in space, and we trained a machine learning model to take photos of all those different transits that I mentioned earlier and find new planets. And lo and behold, we were excited to find 2 as part of the Kepler series. So how it actually works is once we get all of those light curves that I talked about with those periodic dips, we train our machine learning model based on that, and we tell it to say, hey, every single time you see this dip, that's probably characteristic of a star, and I want you to go through this thousands and thousands of data sets that we get from these satellites and be able to identify very clearly, this is a star, this isn't a star, this is a planet, this isn't a planet. And once you're able to make those assertions, it's powerful what machines can do. They're almost 100 times better than humans at identifying this, since we're dependent on our naked eye. But even if these statistics don't excite you, it should be the idea that we're using machines to try and find new worlds so that we can explore them further. And this has never been done before in the history of humanity, because it seemed to be that machines would be extended away from astrophysics, and that most of the analysis that you would do with computational backsides is to do simulations. But now we're actually using the statistical capabilities of these artificial intelligence and neural network models to try and identify patterns better than humans can. And it's this pattern recognition ability that machines can do X times greater than we can. Now, let's talk about how it actually works around in real life. So it's all easy to say that when we try and find these dips, machines can say, yes, this is probably a planet, no, this isn't, and make conclusions. But these dips are never really as nice as we like to see them. Now, they often look like this, which is the initial data set that we had from the MIT TESS telescope, and we have to try and do different things to it. We have to try and flatten it so that the machine can look at it better. We have to run different linear regression models to sort of amplify the distance. But when you rationalize all of this data and you feed it into a machine, the output is quite beautiful. It tells you, yes or no, this is probably a planet, and it gives you a probability estimate of it. That, hey, 85% of the time, based on the model that you've trained it at, this might be a planet, you should look at it further. And we feed this data onto NASA, and then NASA goes on to confirm it through their external measurements that this is likely a planet or this isn't, and then we're able to celebrate. By the way, one of the hidden excitement pieces about finding planets is that you get the naming rights on them. So if you end up discovering a planet, you have entire rights to name it whatever you want. You can name it, I think it would kind of be arrogant to name it after yourself, but you can name it I don't know, after a girl that you've been trying to go after, and then now if you want to take her on a date, you could be by a bridge looking up at the stars and being like, hey, you see that planet up there? That's my planet. And it would make a really iconic pickup line. But beyond that, what it does further is that it actually excites people about what humanity can do with machines. By integrating the two, you're able to do powerful things that you weren't ever able to do before, like find which planets are hospitable for life. In this, you see that if the planet is too close to the mother sun that it's orbiting, then it's too hot, the atmosphere is too dense for us, and human beings can't survive on it. But likewise, the converse is true in that if the planet is too far away from the mother star, it's too cold, and it's like Neptune. And the atmosphere isn't hospitable for human life, nor are the materials and the minerals on it. So you need to be in that ideal distance, and we call that the Goldilocks zone. And the Goldilocks zone is really exciting because planets that are present on it are ones that we can eventually hospitalize or look at further to see if the conditions for life are necessary. And it's just much more exciting to imagine what these planets look like, because for some of them, they're so close that if there was plant life on there, photosynthetic pigments would not be green like what we see in the world today, but they'd actually be red. So imagine that. You'd have entire forests that are red. How beautiful would that look? It'd make for a nice Instagram photo for sure. But just beyond that, it's the whole idea that machines don't necessarily have to separate humanity, that artificial intelligence doesn't have to act as this barrier that splits humanity between the technologically savvy and those that aren't. Rather, we can use it in conjunction with science to accelerate the rate of scientific discovery and make exciting promises like this to see different parts of the world beyond just astrophysics. You can make these applications in the life sciences and in chemistry as well to do protein folding. But there's just so many exciting applications for machine learning to take place in the different fields of science and ultimately unite humanity together for the greater cause. Thank you.